All right, everybody. Thank you so much for waiting, and sorry for the technical issues that we have today. So we have the privilege to have Joel Meyers. So he's an associate professor at Southern Methodist University. So we have a connection here with somebody in the department. So he is the former postdoc advisor of Joe back there. So it's nice to have him here. So just to give you a little bit of the background, so he did his bachelor in physics in the University of Wisconsin, and then he moved to the University of Texas at Austin and worked with the one and only Steve Weinberg, where he did his PhD. And then afterwards, he was a senior research associate at CETA in Canada, and then he got the current position that he has as associate professor in Dallas, Texas. So he's going to be talking today about detection of neutrinos in cosmological observational techniques. Thank you.
Excellent. All right. Thank you, Enrique, for that introduction, and thanks so much for the invitation to be here. As Enrique said, I'm going to talk today about the cosmic neutrino background and observations of cosmology that, let me just see if I can ignore that. Okay. Observations in cosmology that give us insight into neutrino physics and perhaps beyond that. So cosmology is the study of the whole universe, the universe at large, its history, contents, and evolution over 13.8 billion years of cosmic history. We as cosmologists pride ourselves in the fact that we are able to describe with quite high detail these 13.8 billion years of cosmic history. We have a physical model with percent level constraints and all the parameters that define this history. And much of that is owed to observations of the cosmic microwave background, this afterglow of the Big Bang that has propagated to us mostly unhindered for 13.8 billion years of cosmic history. The cosmic microwave background carries with it imprints of the conditions as they were about 380,000 years after the onset of this hot Big Bang evolution. But as we will see, it also is influenced by the stuff that intervenes between us and this surface of last scattering. And our observations are now becoming precise enough that we can use not only this primary information, but also the imprints of the stuff that intervenes to go beyond what we've already learned about the history of the universe and to probe physics beyond the standard model. And what I'll focus on today is how we can use observations of the cosmic microwave background to learn about another background, the background of cosmic neutrinos, which decoupled from the thermal plasma even earlier than the photons that make up the cosmic microwave background, about 1 second into the evolution of the universe, and which have been propagating to us mostly freely ever since. Now, what we'll see throughout this talk is that cosmic neutrinos have a gravitational influence on the evolution of the universe that shows up in the CMB, and also on the growth of structure, which then is subsequently imprinted in turn on the cosmic microwave background as well. And so I will carry you through in this talk how we use the CMB to infer the presence at early times and at late times of these neutrinos, and how it allows us to make a measurement of the absolute mass scale of neutrinos and why that's important. So as I said, we have arrived at a place in the precision of our cosmological observations that we finally have in hand all that we need to achieve a measurement of the absolute mass scale of neutrinos at the level where we would expect to make a detection, even if the neutrinos had the minimal possible mass as inferred from neutrino oscillation experiments. I'll come back and say more about this a little bit later, but we know the mass squared splittings between the mass eigenstates of neutrinos, and if you take the lightest one to be 0, that sets a scale for the minimal sum of neutrino mass eigenstates, which is 58 millielectron volts. And right now, we have in hand the cosmological precision necessary to make a measurement of the mass scale of neutrinos with about that level of precision, about 58 millielectron volts. And when you put all of this together, when you put together the observations that we require, what we see is that the sum of neutrino masses is observed to be less than about 64 millielectron volts. And like I said, this uncertainty is approaching the level where we expect to make a detection. So that all seems well and good. However, what you'll notice is if you look carefully here, this upper bound is actually uncomfortably tight in two different ways. In one, this is tighter than what you would have expected given the volume of data that we have. So this is actually tighter than what we would have predicted before we had the data in hand. Secondly, what you can see is that the likelihood, the posterior, peaks at 0 neutrino mass. And so this actually favors a mass lower than the minimal value of what we infer from terrestrial experiments. Yes?
So this data from cosmological observations, is this bound on neutrinos or all possible light species?
This particular measurement is bound on all contributions that come from light species which were relativistic at early times and non-relativistic at late times. I'll say much more about that throughout the talk. This, strictly speaking, is not just about neutrinos, but all things, yes. All right. So something a little bit fishy is going on here. And in fact, it's even worse than I've sort of pointed out so far, because if you allow for this neutrino mass parameter in cosmology to take negative values, what you find is that the data actually prefers that this peaks at negative values. That the sum of neutrino masses as inferred from cosmology is negative 160 millielectron volts. And this measurement then disfavors the minimal mass for the normal hierarchy at about 99% confidence. Okay? So you would be excused for asking, what do I mean by negative neutrino mass? And most of what I will tell you in this talk is how we actually go about making this observation such that you can interpret what is meant here by the statement that cosmology prefers a negative neutrino mass and what that might be telling us about either neutrinos or the physics of something else. Okay? So this is sort of the punchline of the observations, and I'll tell you how we get there and what it might be telling us throughout the rest of this talk. So let me start with some background on the CMB, the cosmic microwave background, which is one of the key observables that we use to make this observation that I'm talking about. So first of all, the cosmic microwave background is the afterglow of the Big Bang. It's the radiation that's left over from the early period of the universe when it was in a hot, dense state that was filled with an opaque plasma. As the universe transitioned to be filled with transparent gas, the photons that had been rattling around with the plasma in the early universe were free to propagate. And because they were in thermal equilibrium prior to that transition, we expect that the background of those photons has a thermal spectrum, which we observe to a very high precision. These are observations from COBE Fire-Apps, and these are the error bars. These are real data with a perfect 2.725 blackbody superimposed. And these error bars are 400 sigma error bars. So there's an extremely tight agreement between perfect blackbody spectrum and the observations we make of the cosmic microwave background. So in some, so it's very, very strong evidence that our universe evolved from a thermal, hot, dense state in the distant past. Okay. Now, we can go far beyond just measuring the temperature of the cosmic microwave background and look at the deviations from the uniformity in the sky. So we see the CMB in every direction we look in the sky, but it's not exactly the same everywhere. There are slightly different temperatures in one place versus another, and that is due to the fluctuations that existed in the primordial plasma around the time of recombination. Sound waves propagated through that plasma, and the way those sound waves propagate is dependent upon the constituents that made up the contents of the early universe. What I'm showing here is an animation of a single sound wave where you've perturbed the plasma at one specific place, and then you allow that sound wave to propagate outward through the various constituents of the early universe: dark matter in black, gas in blue, so those are the baryons or the baryons including the electrons in blue, the photons, and then the neutrinos in green. And what you can see is that this animation starts with a perturbation here at 0 radius. And so you can think about this as dropping a stone in a pond, and the waves propagate outward from that initial disturbance. And you can see it propagates differently in the different constituents. At early times, the red and blue, the gas and the photons, are tightly coupled. And then right there, at redshift of 1100, 380,000 years into the evolution, the photons and the gas decouple when the universe transitioned from being filled with a plasma to a gas, and the photons became free to propagate. What we see in the CMB is a snapshot of the universe at that instant. When the photons in the gas separate, the photons are then free to propagate. And so what we get when we look at the CMB is a picture of the distribution of stuff as it was at that instant of recombination. Okay? And of course, what we see in the sky is not a single set of ripples on a pond, but rather there were fluctuations everywhere. And apologies, I am guessing I lost connection here. There we go.
Oh, no. Well, maybe we can.
Okay, so what we see is not a single pattern of ripples from a single disturbance, but rather a superposition of such perturbations all across the whole sky. In the early universe, there were different regions that were slightly overdense or slightly underdense, and so what we see is a snapshot of a bunch of superimposed ripples, as shown here. So you can start with, a slice through one such bubble where that would be propagating outward from an overdensity, and then you superimpose all sorts of overdensities and underdensities, and what we see is a pattern that more or less looks like noise when you stack these all together, but importantly, the statistical information about those sound waves are still recorded in that map. And what we then observe when we look at the cosmic microwave background is the superposition of all of those ripples, and as I'll say in a minute, we can extract information about the contents of the universe by the statistical properties of those fluctuations. There's one more important piece of the observation, which is that in addition to these temperature fluctuations, the hot and cold spots or the red and blue spots on this egg-shaped thing, but we also get linear polarization. The photons are linearly polarized, and we can separate that linear polarization into two different types. There are E-mode polarizations that are parity even. You get the same pattern of E-modes when you look at it, and when you look at it in a mirror, it doesn't change its sign. And B-modes, the parity odd patterns, where if you look at it in a mirror, you reverse the sign, you reverse the pattern. The important distinction between these E-modes and B-modes is that scalar fluctuations, density fluctuations in the primordial plasma, produce only E-mode polarization, but gravitational waves produce both E-mode and B-mode polarization. And so one of the key targets of ongoing cosmic microwave background observations is the search for primordial B-mode polarization, which would be a strong indication of the presence of primordial gravitational waves, as would expect it to be sourced by cosmic inflation in the early universe. Okay? I won't focus on inflation in this talk, but I will use this distinction between E and B modes a little bit later. Now, to extract information about the universe as it was at those early times, we look at the statistics of these fluctuations. So we take a map of the whole sky, and just to be clear, this map of the whole sky in this egg-shaped pattern, this is called a Mall-wide projection. What this is just the sphere of the CMB around us stretched out into a flat surface. So the galactic plane lies across the equator here. This is the north celestial pole and the south celestial pole, and then the edges are identified. So this point over here is the same as this point over here. It's just the way that we map the sphere so that we can see the whole thing at once. Okay? And so we take these fluctuations across the whole sky, and now we're not so interested in the fact that there's a cold spot here and a hot spot here. We're rather interested in the statistics of those hot and cold spots. And so what we do whenever we see something that looks more or less like noise is we take the Fourier transform, or in the case of a spherical distribution of data, we take the harmonic transform. And what we get as a result of that is what's called, when we do that for the two-point function, the two-point correlation function, we get the angular power spectrum, which is shown here. So the angular power spectrum of the temperature is this characteristic set of curves with a set of bumps and wiggles, and those bumps and wiggles are the harmonic content of the sound waves that influence the distribution of fluctuations on the sky. And those bumps and wiggles carry information about the contents and process by which those density fluctuations were imprinted on this map. And then the same is true for the E-mode polarization, and then the B-mode polarization, as I said, only comes from primordial gravitational waves, and those are way down here. Okay? Now what we do with these bumps and wiggles is we infer what the universe must have been made up of in those early times and how it's evolved since. If you change the amount of baryons or change the amount of dark matter, you get a different pattern of bumps and wiggles. And so what we can do is take these bumps and wiggles, and this is real data from various CMB observations, and we can infer what the model of the universe would have to be consistent with those statistics. All right, and so what we get when we do that is a model of the universe, which we call the flat lambda CDM model. This is a universe which has spatially flat hypersurfaces, which is dominated by some form of dark energy consistent with the cosmological constant, where about a quarter of the total mass density of the present universe is made up of some form of cold, dark matter that's outside the normal, ordinary matter that makes up the stuff of everyday experience. Okay? So this story is a big success of what we've done with CMB cosmology over the past couple of decades. And what I will talk about for the remainder of this talk is how do we go beyond this to learn more, going past just this standard lambda CDM model, specifically in this case focusing on how we can use observations beyond just the power spectrum to learn about the cosmic neutrino background. Okay. So with that, let me now transition and give you a little bit of background on cosmic neutrinos. So first of all, cosmic neutrinos are light thermal relics from the early universe. So at sufficiently high temperatures, at sufficiently early times, the universe was filled with a hot, dense plasma that was so hot and so dense that the weak interaction was able to hold neutrinos in thermal equilibrium with the rest of the plasma. As the universe expanded and cooled, the interaction rate of the neutrinos with the rest of the plasma dropped below the expansion rate of the universe at about 1 mega electron volt, at which point the neutrinos began a free expansion. And so those neutrinos have persisted throughout the universe ever since, forming a background, a thermal background of neutrinos that influence cosmology in various ways. We have two key observables in cosmology that allow us to learn about the properties of neutrinos. There's a parameter that impacts primarily that encodes primarily the gravitational influence of these neutrinos at early times, and we call this N effective, the effective number of neutrino species. And what this is just a conventional way of talking about the total density of all of the radiation in the universe apart from that of the photons. In the standard model, what that means is it's just a measure of the energy density of the neutrinos. And because the neutrinos were in thermal equilibrium, they make up a very significant fraction of the total energy budget of the early universe. And the influence of those neutrinos on the expansion history show up in our observations. And so we can measure the total energy density of the neutrinos during this early time. The other key observable, and primarily the focus of this talk, is the sum of neutrino masses. So as I'll say more about, massive neutrinos, while they were relativistic at early times, became non-relativistic at later times. And the fact that they behave like non-relativistic matter at late times in the history of the universe means they influence the growth of structure throughout the universe. Now, in the standard model for the minimal sum of neutrino masses, they make up a very small fraction of the total non-relativistic matter in the universe. That fraction is about 0.4% of the total matter density of the universe. But we can see the effects of these neutrinos in ways that I will talk about. But this is just to give you some sense of scale. We're looking for 0.4% of the total matter density in the universe today when we're talking about looking for the effects of neutrinos. All right, so cosmic neutrinos, like I said, are a thermal relic from the early universe. We can understand their properties very precisely just by a simple evolution of the statistical mechanics of the early universe. So as I said, neutrinos decoupled at about 1 mega electron volt. And if we assume for a moment that they decoupled instantaneously, then shortly after that, as the temperature dropped below the rest mass of electrons and positrons disappeared from the thermal plasma, so they could annihilate to produce photons, but the photons were no longer energetic enough to produce electrons and positrons. And that resulted in a heating of the photons compared to the neutrinos. So the electrons and positrons annihilated. They primarily annihilated 2 photons, and therefore heated the photons as compared to the neutrinos. And so we can predict just by using entropy conservation that the cosmic neutrino background should be cooler than the cosmic microwave background by a factor that we can compute, which is 4/11 to the 1/3. Because we measure very precisely the temperature of the cosmic microwave background, we also know the temperature of the cosmic neutrino background. And knowing that tells us everything we need to know about the cosmic neutrinos because it's a perfectly thermal bath of these neutrinos. Specifically, in the early universe, the cosmic neutrinos made up 47.1% of the total energy density of the universe. Okay? This is important because the gravitational influence of these neutrinos shows up in the early expansion history. And so we have a very significant measurement of the presence of this energy density from these neutrinos at early times.
Excuse me, this number, 47%, how does it compare with the previous number you said, a fraction of a percent?
Oh,
currently?
yeah, great. So this is excellent question. So this fraction is the fraction of the total radiation energy density of neutrinos at early times. And the reason this is so much larger than what I said about 0.4% is that at later times, all of the radiation, the photons and the neutrinos, have an energy density which redshifts more quickly than that of matter and of dark energy. And so matter and dark energy came to dominate the total energy budget of the universe at a later time. But the neutrinos are still there, and so they still have a non-negligible impact later on.
Thank you.
All right. I'll mostly skip through this, but I just wanted to briefly say that instantaneous decoupling picture is an approximation. We can be more careful about the way that neutrinos decouple. It's actually an energy-dependent and temperature-dependent process, and so we predict something slightly different than just that 4/11 to the 1/3. And putting that all together, what we find is that the prediction for n effective in the standard model is 3.044. So this is normalized such that if there were 3 species of active neutrinos that instantaneously decoupled, it would just be equal to 3, and so we get something slightly larger than that, 3.044. And for the purpose of this talk, I'll just tell you that observations agree very well with this number. The current observational constraint is like 3.0 plus or minus 0.15. So there's very good agreement and very strong evidence that there was a contribution to the energy density consistent with the presence of the cosmic neutrino background at early times. Okay. Now, neutrinos, we know, have non-zero mass. We know this from flavor oscillation experiments. And what we measure very precisely in those flavor oscillation experiments is the mass squared splittings between the mass eigenstates. However, what we don't measure very precisely, or at all, is the absolute mass scale of neutrinos, nor the ordering. So there are 2 choices for how you can split up these masses. You can have the smaller of the mass squared splittings between the 2 more massive states, or between the 2 lighter states. And those choices are called the inverted ordering or the normal ordering. And in each case, if you take the least massive of the neutrinos to have 0 mass, that predicts the minimum of the sum of the neutrino mass eigenstates. And the reason I'm talking about this quantity is this is the quantity to which cosmology is sensitive. In the normal ordering case, the minimal sum of neutrino masses is 58 millielectron volts. And in the inverted ordering case, it's about 100 millielectron volts. So this sets the scale, the precision with which we need to be sensitive to the parameter sum m nu in order to make a measurement that we expect to see in cosmology. Now, cosmology is sensitive to this quantity largely because the cosmic neutrino background is at a very, very low temperature, which means that because we know these mass squared splittings and we know the temperature of the cosmic neutrino background, we know that we have at least 2 eigenstates which are non-relativistic today. The temperature of the cosmic neutrino background is below at least 2 mass eigenstates today. And furthermore, these cosmic neutrinos are very abundant. There are about 112 per cubic centimeter per species of neutrinos passing through your body all the time. So there are 112 per cubic centimeter of each species. And what that means is cosmology provides us with a huge abundance of non-relativistic neutrinos, which is a very unique situation because every time we interact with neutrinos, they're produced in processes that take place at energy scales on the order of hundreds of keV or mega electron volts, where these masses are on the scale of millielectron volts. And so cosmology provides us with non-relativistic neutrinos, and so we have a hope to look for the effects of neutrinos in the regime where their mass is important. Okay. The effect that we hope to see in cosmology from massive neutrinos arises from the fact that they were relativistic at early times, moving very rapidly at early times, but they were non-relativistic at late times. And as a result of that, they don't cluster the same way that cold dark matter does, or that baryons cluster. Specifically, neutrinos act like hot dark matter. They retain large thermal velocities that they inherited from being a thermal relic of the early universe, and they're non-relativistic today, so they contribute to the matter density today, but they don't cluster the same way as the rest of the matter. And as a result, in a universe that contains massive neutrinos, compared to one which contains only massless neutrinos, what we predict is a suppression of a quantity that's called the matter power spectrum. This matter power spectrum just tells us about the variance of clustering as a function of wave number k. So going to the right is smaller scales, so it's higher wave number, smaller physical scales. And to the left is smaller wave number, larger physical scales. And then this number is much like the temperature power spectrum, just tells us about how prominent are fluctuations on that scale. And in this case, we're talking about fluctuations in the matter density. And in a universe that contains massive neutrinos, we expect to see a suppression of matter clustering on scales smaller than the length over which neutrinos free stream. Okay? So this is a characteristic suppression of clustering on small scales that we expect to see in the presence of massive neutrinos. It's this suppression that we're going to look for in cosmology to infer the presence of massive neutrinos. Okay?
And in this scale, the neutrinos are not interacting with each other. That's free.
That's correct. Yes. Here, this assumes free neutrinos, which would be what you'd expect for the standard model. Yeah. Mm-hmm. And so just to remind you, the fraction of neutrinos, the fraction of the non-relativistic matter in the form of neutrinos is about 0.4% in the minimal scenario. This suppression is on the order of a few percent. So you might ask, where did that extra factor come from? And I'll say more about this a little bit later. But the neutrinos actually suppress the clustering. Not only do they not cluster themselves, but they suppress the clustering of the other matter in their presence. And so that leads to an enhancement of this factor of 8. And so we're looking for an effect that's on the order of a few percent when we're looking at these cosmological observables. Okay. All right. So now we know what signal we're looking for. And let me tell you a little bit about how we actually go about measuring it. And before I get there, let me also just take a brief detour to tell you why you should care at all about measuring the neutrinos, the massive neutrinos. So the simplest answer I can give you is that we know that neutrinos have mass, but we don't know what it is. It's really difficult to measure in the labs, in terrestrial experiments, so it would be wonderful to measure it somewhere. That's perhaps not so satisfying, so let me give you better answers. One reason that we care about measuring the absolute mass scale of neutrinos is that it sets a clear target for other experiments that we can conduct. For example, there are searches for things like neutrinoless double beta decay that depend upon some combination of neutrino masses. And if we measure a particular mass scale of neutrinos in cosmology, that sets a clear target for what we hope to achieve in those neutrinoless double beta decay experiments. More generally, a measurement in the neutrinoless double beta decay experiment can be compared in a plot like this to see that everything is consistent, or maybe if we combine those things, we're getting a hint of something beyond just the effect of neutrino mass. So roughly speaking, lab-based measurements are very complementary to what you can do in cosmology. It's also very relevant for cosmology in and of itself because, as I've sort of alluded to already, the measurement of neutrino mass in cosmology relies on the behavior of the neutrinos from very early times in the evolution of the universe and seeing their effect at very late times in the growth of structure. And so this is really an end-to-end test of cosmology to see the effects of neutrino mass show up through cosmological observables. And furthermore, it need not just be neutrinos that could lead to this suppression of structure that we're talking about. Any light species with a non-zero mass, which was relativistic at early times and non-relativistic at late times, would also contribute to the suppression of structure growth in the way that I've discussed. And there are concrete examples of this, like gravitinos, which arise in various models of supersymmetry with various breaking schemes where you might expect to see the same effect show up. So any bound that we put on the mass of the neutrinos naturally bounds other extensions to the standard model, and we get that all in one fell swoop by doing this sort of analysis. Another reason you might care is if you care about the structures within the universe. All of these things that we're talking about set the initial conditions for the way that clusters of galaxies or large-scale structure or galaxies themselves grow. And if we're talking about changing the amplitude of clustering on the scales on which those objects grow, you will change the predictions for what you will see when you go out and look at galaxies or clusters of galaxies or this sort of thing. And so it is degenerate, the mass of neutrinos is degenerate with other parameters that you might like to infer from those astrophysical analyses. And so if you care about doing precision astrophysics, you need to understand what is the mass of neutrinos to set the appropriate initial conditions for those studies as well. Okay. All right. So how is it that we actually go about measuring this suppression of structure imprinted by massive neutrinos? So what we're looking for, again, is a suppression of matter clustering on scales below the free streaming length of neutrinos. What I'm plotting here is a plot showing the sensitivity we have to the matter power spectrum as a function of redshift vertically and as a function of wave number horizontally. So for higher redshift, we're talking about earlier times. Lower redshift, we're talking about later times. Redshift 0 is today. And then again, wave number is smaller scales to the right, larger scales to the left. The scale of the free streaming length of neutrinos is shown here in this purple dashed line. And so what we expect from the neutrinos is that things to the right of this dashed line will show a suppression of clustering due to the free streaming of neutrinos, and things to the left will not show the suppression. And so what we want to be able to do is to measure the matter power spectrum to the right of this line in a regime where we can calculate things reliably. And there's one more line I put on here, which is the division between scales where we can use linear perturbation theory to the left of the red dashed line, and scales where we need to rely on simulations in practice to calculate the observables to the right of this dashed line. And so what you can take away from this is that we have a lot of sensitivity in the regime of interest from CMB lensing. Okay? And so I'm going to focus, for that reason, for the rest of this talk, on measurements of the suppression of the matter power spectrum using CMB lensing. Okay. All right, so CMB lensing.
Sorry, what is the colors? No, the colors. No, so what represents the bumps? So this is the sensitivity of the measurement. So on which scale?
Yeah, it's the sensitivity. So there are a bunch of slices in redshift, and this is the signal to noise weighted sensitivity of each of these experiments, CMB lensing, galaxy density, or cluster counts, that it has in that range of redshift and of wave number. So in other words, like galaxy cluster counts tell you a lot about small scale physics, and then it kind of peters out as you go to higher redshift. Galaxy density has this kind of shape. You have sensitivity primarily on small scales, then it goes to slightly larger scales, and then peters out when you can't see the galaxies. And then,
And matter power relates to the brightness of the CMB, or how do you measure this matter power?
So the matter power from the CMB is going to come from CMB lensing, which I'll describe in more detail in just a second. For the other things, galaxy cluster counts, that would have to do with just how many clusters there are, and that has to do with how clumpy the matter is, which is what the matter power spectrum tells you. Okay. All right, so CMB lensing. So this is the way that we're going to measure the matter power spectrum using observations of the cosmic microwave background. So what I'm showing here is a simulated little patch, a little 5 degree by 5 degree patch of the cosmic microwave background in the absence of lensing, and I'm showing the E mode polarization here and the B mode polarization here. I've simulated a universe with no primordial gravitational waves, so the B modes are just 0, and I'm going to lens it with a lensing potential that looks like this. And when I apply the lensing, so the most obvious effect, this is now the lens CMB, the most obvious effect is that the B modes are no longer 0. And you can also see that the E modes have changed. You can convince yourself that if you look at both of these plots, that the lens B modes are correlated with the E modes you started with. But you can see the effect on the E modes if I flip back and forth. You can see that various regions of the E modes are magnified and demagnified. And that has to do with the structure that intervenes between us and the surface of last scattering. So gravitational effects bend the photons of the cosmic microwave background to make particular areas of the sky look larger or look smaller. And that's the effect of gravitational lensing that we're talking about. And we can use the change to the statistics of the observed CMB to infer the presence of that stuff that intervenes between us and the surface of last scattering. Okay. When we do that, what we get is a map that looks like this. So this is, again, a map of the whole sky. This big cutout in the middle is where we don't have good data because the galaxy intervenes between us and the surface of last scattering. But above and below that, what we see are these bright and dark patches give us a measure of the integrated mass density between us and the surface of last scattering along any particular direction in the universe. Now, because the matter density is dominated by dark matter, you can actually think about this as a map of all of the dark matter in the universe integrated out to the surface of last scattering. Okay? So this is a real observation, and it comes again from measuring this change in statistics when you look at any particular direction in the cosmic microwave.
And bright spots, the whitest regions, have higher density, or the blue regions have higher density?
The white regions have higher density.
Okay.
Yeah. Mm-hmm. That's right. Okay. All right, so this is a 40 sigma observation, and this is getting ever better with higher precision observations as we go to smaller scale observations.
What is it that's 46 sigma?
The overall detection significance of this lensing signal as shown here. So you might complain that if it's only 40 sigma, a lot of this is noise because you shouldn't be able to see a patch that's this size, for example, if you only have 40 sigma observation. Sorry, so I'm going into too much detail. 40 sigma observation is just the statement that we measure this lensing effect with significance of 40 sigma. Okay. Future observations will drastically improve our ability to map out this lensing and therefore infer the effects of the matter that intervenes between us and the surface of last scattering. So this is a forecast for an experiment with the precision of something like CMBS4. And because that matter power spectrum influences the gravitational lensing power spectrum of the CMB, the imprint of the neutrinos, which is this suppression of matter power on small scales, shows up also in the CMB lensing power spectrum. So what I'm showing here is the change to the lensing power spectrum due to the massive neutrinos compared to what the power spectrum would have been in the absence of massive neutrinos as a function of multipole. So again, this is smaller scales on the right, larger scales on the left. And then you can see that there's this characteristic suppression of matter clustering now viewed through the CMB lensing power spectrum. And what you can see is that at the precision of something like CMBS4, it should be very easy to distinguish the suppressed matter power spectrum from one that is not suppressed. However, there's a caveat to this, which is that we can only use this measurement of the CMB lensing power spectrum to infer the neutrino mass if we know what it would have been in the absence of neutrinos. Okay? And what that means is that there are some significant degeneracies that we have to account for in order to translate this amplitude measurement into a mass of neutrino measurement. Okay? And there are two important degeneracies that I'll mention here. I'll go kind of quickly through this because I realize I'm running out of time. One is that the optical depth to reionization, which has to do with rescattering of CMB photons relatively nearby after all the first stars and first galaxies turned on, changes the amplitude of fluctuations we see in the cosmic microwave background. This is important because in order to set this scale, we need to know how big were the density fluctuations to begin with. And the way we best measure that is through the amplitude of the fluctuations in the temperature of the CMB, but that's degenerate with how much they got rescattered because that will mute out those fluctuations. And so this is almost totally degenerate with the primordial amplitude, except for this bump down here on large angular scales of the E-mode polarization. And so this bump allows us to disentangle the optical depth to reionization and the primordial amplitude of fluctuations. One challenge with that is the only way we can measure this bump effectively is from satellite observations of the cosmic microwave background. And so we rely on the observations from the Planck satellite from 2018, which gives us this measurement with on the order of a 10% error bar, 15% error bar. And this is the best that we will have for quite a long time to come. So this is one challenge that we have, is that we just have to rely on these satellite observations.
And the blue curves are theoretically predicted or measured?
These are all theory, just to show you that you can trade off optical depth for a variation of the primordial amplitude, except for in this bump.
I see.
Yeah. Okay. The other significant degeneracy has to do with the total amount of matter in our universe. So if you change the total amount of matter, it changes how much it has clumped throughout the history of the universe. Now this we can measure very well with observations of the expansion history of the universe, and in particular spectroscopic galaxy surveys which map out the expansion history, which are primarily, or the way that they're kind of sold is that they can measure the influence of dark energy on the expansion history, are also very good at pinning down the total amount of non-relativistic matter in our universe. So this is a plot from the DESI collaboration, Dark Energy Spectroscopic Instrument. And what they measure is the characteristic scale associated with baryon acoustic oscillations acts as a standard ruler, and they measure how big that ruler is across the history of the universe. And that allows them to map out the expansion history of the universe, and thus pin down the total amount of matter in our universe, which is the other ingredient we need to calibrate this line and translate the CMB lensing measurement into a measurement of the mass of neutrinos. Okay? And it's for this reason that we needed these baryon acoustic oscillation measurements from DESI that we just now have enough of the data to piece together to make a measurement of the mass of neutrinos. So when you put that all together, as I said, what you get when you look at all the data available, the best data available, and you measure the sum of neutrino masses, what you find is that you get a negative sum of neutrino masses. Okay? But now, having gone through how it is we make this measurement, we can infer, we can understand what this measurement actually means. The fact that this quantity is negative, what it's telling us is that we see not a suppression of matter clustering on small scales, but rather an enhancement of clustering compared to what we would have expected in a universe with only massless neutrinos. And that observation then allows us to try to figure out what could have been causing this enhanced clustering. It may have to do with the neutrinos, but it may have to do with something else. And so that's what I'll turn to next. Okay. There's one more thing that I should say, which is that in addition to the impact on the clustering of matter, the neutrinos themselves also impact the expansion history. In particular, neutrinos behaved as radiation at early times and as non-relativistic matter at late times. And the way that the universe expands is related to the total energy density of the universe. And massive neutrinos dilute differently than do massless neutrinos, which always behave like radiation. And so that change in behavior from massless to massive, from radiation to matter-like, also impacts the expansion history. And so you can try to disentangle these effects of massive neutrinos on the expansion history and on clustering. And when you do that, you can parameterize the effect on expansion history through this parameter I call mu BAO, and on clustering, mu clustering. And what you see is that if you constrain both of those parameters simultaneously, you get a preference for negative values of both with some degeneracy among them. Physical neutrinos would be restricted to a line where these quantities are equal, this dot dash line going like this. And furthermore, they would be restricted to values that are positive. So physical neutrinos would live up here, and then the minimal neutrino mass lives right there. And the data shows a preference for this blob. Okay? All right. So let me now explain, or try to explain what could be going on in the data. Why are we seeing negative neutrino mass?
That means there's more clustering in the short range.
That's right. There's more clustering than you would expect in the standard cosmological history. So I'm going to start with the boring explanations. One possibility is that one of those things that I said is degenerate with neutrino mass was just measured incorrectly. So the optical depth, maybe there's a bias in our measurement of the optical depth. This plot basically shows the evolution in history of the observations of this quantity tau, and you can see that it hasn't remained all that stable. And as I said, we're sort of limited by relying on measurements from CMB satellites to make this measurement. And you can see even from Planck, there are different analyses that have slightly disagreed. But what I can say from this plot is you'd have to shift it to get all the way back to the minimal sum of neutrino masses just with a shift to tau. You'd have to move this point all the way up here, which is larger than just a statistical fluctuation. Okay, so you'd have to move this all the way up. So there would have to be a systematic error and not just a statistical fluctuation to account for it this way. Okay. But it's possible that there's a systematic error that's exists in all these data points, and maybe the true value is up here. But that means that the analysis was wrong somewhere along the way. Another possibility is maybe we've measured the matter density incorrectly from the baryon acoustic oscillations. This is the same sort of plot showing the history of these observations as inferred from various galaxy surveys. And what you can see is that with spectroscopic surveys, these things have remained more consistent. But again, to shift it all the way back to the minimal neutrino mass, you'd have to shift this point all the way up here. And again, it would have to be not just a statistical fluctuation, but a systematic error. Okay, so those are kind of the boring explanations, but it is possible that one or both of those contributes to what we're seeing. The other possibility, the more exciting possibility, is that this excess clustering really reflects new physics beyond the standard model. And maybe that's related to neutrinos, maybe that's related to something else. But let me just say, I already sort of mentioned this, that the suppression that arises from the mass of neutrinos actually has two contributions. One is that the neutrinos themselves don't cluster. So there's a fraction of the non-relativistic matter which does not cluster, and that just comes here in a way that you can kind of see if, anyway. The other piece is this log-enhanced behavior which accumulates over cosmic history. This is the fact that dark matter clustering, all the rest of the matter, doesn't cluster as strongly in the presence of the massive neutrinos. And this is because the massive neutrinos contribute to the expansion rate like non-relativistic matter, but don't source the potential well into which the other stuff can fall. And the reason this is important for thinking about new physics or additional physics that might contribute to this excess clustering is that this has accumulated over a long period of time. Specifically, it's accumulated ever since the neutrinos became non-relativistic, which was around a redshift of 100. So at very early times after recombination, neutrinos became non-relativistic and have been accumulating this suppression of structure growth throughout most of the history of the universe. So that limits your flexibility in terms of model building for how you might counteract this effect. Let me just very briefly say that dark energy, evolving dark energy, is very unlikely to be the solution to this problem. So you may, if you followed what's going on with the DESI results, there's been a lot of excitement about the possibility that dark energy may be evolving. And so this plot is basically just demonstrating that that's unlikely to be the explanation for why the neutrino mass is favoring negative values. And I think I'll kind of skip it here just in the interest of time, but I'm happy to say more about it if people are interested. Okay, so there are a host of solutions that you could explore that would bring the neutrino mass to 0. So specifically, the neutrino mass only shows up in cosmology if the neutrinos persist throughout the history of the universe. You could imagine that if the neutrinos themselves are just not stable, if they undergo decay to some massless species, then they would behave cosmologically as if the neutrinos had no mass. So if they didn't stick around, you could bring the contribution of neutrino mass to cosmology down to 0 by having them either decay or annihilate. Another possibility is that you've either heated up the neutrinos so they remain relativistic throughout the history of the universe, or cooled them down enough such that they do behave as cold dark matter and not like hot dark matter. Or it could be that the neutrino mass that we observe terrestrially is an environmental or time-dependent effect. Maybe the neutrinos only get their mass in the presence of the galaxy or the Earth. And in which case they would contribute to the neutrino mass experiments terrestrially, but not cosmologically. All of these solutions might allow you to bring the inferred neutrino mass down to 0 from cosmology, but they can't get you to negative mass because none of these things enhance clustering. All right. In order to enhance clustering, we need something else going on. And it turns out that probably the easiest ways to enhance clustering don't have anything to do with neutrinos themselves, but maybe it has to do with the clustering of the dark matter. So one concrete possibility is that maybe the dark matter experiences a force beyond just gravitational attraction that causes it to cluster. Maybe the dark matter exhibits a long-range force that acts as if the dark matter is subject to stronger gravity than the ordinary matter. And so you can imagine there's a long-range dark force that causes dark matter to cluster more. So this plot basically shows how such a model affects both the expansion history, because this new long-range force must be included in your evolution equations, so it affects the expansion history and the clustering. And what you can see is that it does kind of go the right direction, but it's not all that great of a fit to the data. Other possibilities include a modification to the initial statistics. So maybe we are mismeasuring our lensing amplitude because we assumed something about the statistics that there was purely Gaussian, but maybe there was something going on in the initial conditions that made it look like excess lensing. Or it could be that some new physics like cosmic birefringence could also show up like lensing. And so that would also require some new physics that could impact either the lensing or the optical depth. So we explore in our series of papers a whole host of these kind of new explanations. One kind of interesting thing about all these possibilities is that they make predictions that would show up elsewhere. So it's not just that you have to rely on improving all the data that I'm talking about here, but if you have a new long-range force for dark matter, for example, that would show up in the clustering of galaxies. That would show up in things like the bispectrum of galaxy density if you tried to observe that kind of thing. So all of these possible explanations, even though we've been motivated to think about them because of this negative neutrino mass, make predictions for a signal that you can look for elsewhere. Okay. So I think I'm at the end of my time, so let me just wrap up by saying that the cosmic microwave background has been really valuable in our understanding of the history and evolution and contents of the universe. There's a lot more to get out of those kind of observations, including new insights for particle physics, cosmology, and astrophysics. And so let me just go ahead and stop there. Thanks very much.
Thank you, George, for the next talk. So any questions?
Could you go back to your slide 27, the one, 27, yes. What would this curve look like if your measurement, let's say, was is what you expect?
Mm-hmm.
I mean,
Yeah.
you would expect this line to be moved over to where the
Exactly. You'd expect this peak to sit right on, well, depending on what the mass actually is, you'd expect this peak to be somewhere in the positive regime, and at a minimum, it would be at 58 millielectron volts. Could be higher, but you'd expect this peak to sit right on 58 or above.
And you won't settle for anything until you get it there, right?
Well, I think, so that's a good question about the sociology of science. I don't think it's a question of, we don't need to tweak the data just to force it up here. This really could be reflecting something that we're missing in the modeling, which would be exciting, or it could be a bias that's
Does it have anything to do with the tension between Planck and WMAP?
So that's a good question. There is one such tension that I sort of vaguely alluded to here. So the tau measurement does exhibit this tension between Planck and WMAP. So the orange points are all WMAP, the blue points are all Planck, and one significant difference is you'll notice they agreed here, then they recalibrated and it went way down here. If it was the WMAP value for tau, this tension would effectively go away. Now, usually that's not the tension people talk about between WMAP and Planck, but that is one such discrepancy between these things that it could bear on this discussion. Yeah.
And Alexei, then.
So some people propose that neutrinos interact with photons more strongly, like polarizability of neutrino could be induced by new physics.
Yeah.
What effect would it be on this analysis?
That's a good question. I'm not sure that I have a plot. Okay, let me say one thing that could result from it. This is not something I talked a great deal about in this talk, but there's an effect of neutrinos on these spectra, which is associated not just with their mean density, but with the fluctuations in the neutrinos themselves, in the neutrino density. And what that impacts is the peak positions of these spectra, and specifically the free streaming of the neutrinos causes a shift in the peaks beyond on small scales. If the neutrinos interact with either themselves or with photons or both, then they don't free stream in the same way, and so you would predict a slightly different shift of these peaks or no shift at all. We observe that shift at reasonably high significance to rule out very strongly self-interacting or neutrinos that interact with the photons. It's entirely possible that the window that you're referring to is still open from cosmological observations, but that is a way that we can constrain whether the neutrinos are interacting or not interacting with this data.
I want to go back to 27. I had a follow-up question.
Yeah.
On this curve. The width of the green curve, that's a measure of your confidence interval.
Yep.
And so even if we got it shifted over so the peaks match with the dotted lines, you still cover a broad range. How do we make a significant conclusion from that? Or how do you make your peak thinner?
Yeah, great question. So this plot, to be fair, is made with data that's now a year old, and so these error bars are tighter than what I've shown here, but not by a huge amount. And so, okay, so I guess maybe to answer the significance of the tension, currently sits at about 99%. So even though these error bars are wide, the overlap of this curve with the minimal mass is small enough to make it a little bit uncomfortable. The way that we tighten these will be better baryon acoustic oscillation data, which is due next year, better CMB lensing data, which is also due next year, and then better data on the optical depth reionization, which unfortunately is several years off. The reionization optical depth, we will best measure with a CMB satellite. There's a proposal for one to fly in the 2030s that's not totally guaranteed will happen. Those are the three primary avenues by which we can tighten these things.
Thank you.
What would happen, what would it look like if instead of plotting versus some m nu, you plotted versus sum of m nu squared?
So let's see. Because because cosmological data is sensitive to this, the error bars would be skewed. That is, it would no longer be symmetric. So you expect the errors to be symmetric in the parameter to which you're directly sensitive. And then if you plotted it, m nu squared, so negative m nu squared would actually flip you over here. So you'd be somewhere in the positive regime with some skewed error bars, and then these things would stretch out.
So the inferences would be quite different?
They would be different, but I would caution that cosmology is sensitive to m nu and not m nu squared. So you would get a different looking plot, but the interpretation would be confusing because it's actually this parameter and not the square to which you're sensitive.
So I think the answer to my last question would, the inferences would be quite different.
Yes.
And one more question.
Mm-hmm.
The CMB, you talked a lot about gravitational lensing
Mhm.
of CMB.
Yep.
But we have gravitational lenses that are not cosmological, they're just around galaxies.
Oh, yeah.
Has
Mhm.
one measured the CMB gravitational lensing around gravities and around galaxies and seen B mode, for example?
Yes, so you can correlate this CMB lensing map with a map of galaxies, and that gives you additional information, specifically because you know the locations of galaxies in three-dimensional space. What you get from the CMB is just a two-dimensional map, but you can say, okay, here's a spot with excess lensing. Are there extra galaxies in that direction of the sky? And where are they along the line of sight? And so you can actually learn more about the three-dimensional distribution of three-dimensional distribution of mass by cross-correlating this with galaxies. And that has been done. And then maybe to add one more piece of information, you might ask, why do we need the CMB lensing at all? Why couldn't we just use lensing of the galaxies to measure the mass? And you can do that. It's not exactly shown in this plot, but there's you can think about how it would work. This is galaxy density, where you actually count the galaxies and see how they cluster. The lensing of those things would basically just give you additional signal to noise at redshifts lower than each of these samples that you can see. There's a challenge with that, and there's a reason we don't rely on that right now, which is that it's harder to calibrate the absolute mass scale of galaxy lensing as compared to CMB lensing. But in principle, you can combine them, and you're getting at the same underlying information. But there's more astrophysical complication.
Adam?
Before when you showed the lens and unlens, like B modes and E modes, I was just wondering if you know what software you use to unlens it, or if you did that or not.
Yeah, so this is just simulated data. So the specific software I used here was this. This is just a Gaussian random field here and here. Well, 0 and a Gaussian random field. And then the lensing was done with QuickLens, which is a publicly available software package. All it does, just as a practical matter, is this is the lensing potential. You can calculate a deflection, which is just the derivative of this in angular space, and it just moves points. It just takes these points and moves them, not specifically on E and B, but on Q and U, the Stokes parameters, and then you just recompute E and B afterward.
So you started from the unlens?
Yep.
And lensed it?
That's right. That we started from the unlensed and then lensed it just to show the effect. Yeah, but you're asking about.
Go the other way, or?
It is possible to go the other way as well, but you will always experience noise when you do so.
Sure.
So the way that you delens, this is really important for measuring these primordial B mode fluctuations. You can statistically infer a map like this. There will be statistical noise when you do it, but once you have a map, because you know how lensing works this way, you also know how to unlens, how to delens. And so you can remove some of this, but you'll still have some residual B mode lensing, from lensing that remains afterward.
partial.
So, can you go back to that plot of the optical depth? with
Yes.
that Planck and
Mhm.
W? So there was just one scale, one measurement that was kind of overlapping.
Yes.
So is it, I don't know what is planned in future missions, but is it possible to get a mission that can actually test the range of these values and also cover the scales covered by both of these missions?
Yes, so there's a proposal, the specific proposal that has the best chance of flying is called Lightbird. And the primary goal of Lightbird is to measure the primordial B-mode polarization on large angular scales. But if it has any chance of achieving that, it needs to measure all of the relevant scales for inferring the optical depth. To be slightly more specific, all you need to measure that is these large angular scales, this bump right here. So Planck and WMAP were both CMB satellites, both measured these scales with different instruments at different times, and WMAP in particular had poor polarization, systematic control, and noise. Planck did a bit better, but we're really just talking about measuring these large angular scales. Lightbird is the next that should be the one to do it in the 2030s. There's a balloon-based experiment, which again is going to measure the same thing that's proposed, called Taurus, which might fly a little bit earlier, but still we're talking about early 2030s. So those are the prospects to improve tau. Primarily CMB satellites or high-altitude balloons.
And this is probably not at all related, but what happens when the CMB photons pass through patches that are ionized locally?
Oh, yeah, good question. So you can see other effects. So this CMB lensing is one of a category of what we would call secondary anisotropies of the cosmic microwave background. Localized patches of ionized gas also cause distortions in the CMB or modifications to the CMB. Very prominent is if that gas is hot, it leads to a spectral distortion called the thermal Sunyaev-Zeldovich effect. If that gas is moving along the line of sight, it leads to a shift in the observed temperature called the kinetic Sunyaev-Zeldovich effect. If you just have a patchy history of reionization, that leads to modulation of the CMB temperature power and the CMB polarization power along the line of sight. And that can also lead to statistical anisotropies in the ways that we're talking about here. And that's something that we're actively searching for with the current generation of experiments. That peaks at smaller angular scales and has a smaller amplitude than lensing, but the same sort of reconstruction technique can be applied to that patchy reionization as well.
Okay. Patchy reionization itself is not well understood.
That's right. And in principle, the CMB allows us a mechanism to constrain how patchy it was, how big those bubbles were, when it happened, and that kind of thing.
All right, so we passed the time already, so let's thank Joel for the fantastic talk today.